Physical characterization of a surface coating. Now, after this deposition of the coating, it is finally the last stage of the total activity. That means, at this stage we have to evaluate and assess the properties, characteristics and the performance of the coating. So, this is the first step in that direction to know what about the quality of the coating, its property and possibly what would be the possible performance in the actual field. Now, in this case what we have mentioned here as physical characterization. Now, when we deposit a coating, it is finally comes to this, it is process, then structure, that gives the property, and finally the performance. So, what is important here to know exactly what we mean by the structure of the coating, architecture of the coating, and there are various issues we have to look and properly address if those conditions and qualities are not properly made or satisfied. So, that is why this physical characterization of the coating, that is so important before we go to the next step. Now, here what we can see that when it is a surface coating, we can have three types of activities concerning the coating or around the coating. One is that a coating is deposited or produced in a mass production in a routinely matter. It is a routine activity, and in this routine activity, to know whether the process technology is consistent, reproducible, and it can be handled without any difficulty, and it is one of the most reliable technology. Time to time stock taking is important. That means, routine checking on the quality of the coating, that has to be done, and that is why we call it routine quality control, and which is normally done in the industry, the manufacturing unit. Next comes one of the activity, maybe we have one existing coating of a particular material, but some effort can be given to improve its basic property, performance, say hardness, density, wear resistance or corrosion resistance, like that any of those functional property without changing much of the basic material composition. There can be some effort by adding little bit of material or changing the processing conditions. Maybe there may be a organized effort to improve the property, and that is exactly what we call improvement over the existing one. There also we need this activity, that means physical characterization and other follow up activities. Now comes the third one, it is totally new, that means the coating is not known to us, how it will be deposited, on which geometry it will be deposited, what would be the material of the substrate, how many pieces are to be produced, what will be the operating condition for this coating. Now, things are not known, totally a new activity. Even in this case, even if we make some trial run in the laboratory scale, but that is not to suggest that that does not require any of those assessment of evaluation. It is equally important for a coating under development. So, in that case also physical characterization, that is also important. So, we understand three types of coating, one routine, one just little bit of improvement and another is maybe totally new. Now comes the defects in surface coating surface. Now, what are those defects? Let us have a quick scan here. Number one, what we can see, a non-uniform coating. That means it has grown in a very non-uniform manner over the entire substrate, and depending upon some preferential sites we have large growth, and in certain places it is very low growth. We have also what we called outgrowth in certain places, and that looks like a mountain in those areas, very easily identified. Unfortunately, because of some reason, whether it is in the gas phase or say the metal donor or the contamination comes from the reactor itself, it is an unfortunate eventuality and some impurities got into this coating. Then we have, this is also very important to see that there are, this is a coating, but coating does not mean its composition, stoichiometry and like that. There are certain crystallographic planes one like to have parallel to the substrate surface in order to enhance certain property and in order to avoid certain weakness. So, the coating should, in a coating what we like to do to minimize this weakness limitation and to increase its strength. So, there are situations where we may find that certain crystallographic plane of that coating material need to be aligned with the substrate surface, but if it is not the case, then the coating, we cannot expect the coating to give its the very best, and in that case the whole effort will be just counterproductive and the purpose will be totally defeated. So, this is one important issue. Then we have some kind of undesirable phase in the coating. So, this phase is not at all wanted and we have certain thing. So, it is not the question of that bulk percentage of the 2 or 3 components, it is actually in what form it is existing. So, that is also very important issue, that is why we call it this undesirable phase, and that should be detected properly. We have also finally, this is totally a thing, say for example, now we can see crack in the coating, a void we can immediately detect in the coating, porosity in the coating, or it can be even in the coating substrate interface. So, this coating substrate interface, it is not visible once the substrate is fully covered, but we must have some ways and means to examine in that level that would be sufficient to give get clear picture. Well, we have one of the strongest interfaced, most best produced interface and one of the strongest, and that will give the expected or even a better performance with that strongest possible coating and substrate interface adhesion. So, these are the few things one has to look before we can go for any follow up steps in the downstream side, and that has to be taken up in proper manner. Now, with this what we can find here, that is what we call here, this is need of physical characterization of the coating. So, if we have understood that what are the need for these defects to give proper importance, and we cannot just ignore, if we give due importance, then definitely that necessity is immediately felt that need of physical characterization of the coating when one looks into those possible defect which is very unfortunate, but for certain reason sometimes we just cannot avoid, and proper action has to be taken to remove those and to minimize to a very insignificant level, so that those defects we can, for all practical purpose, we can ignore them. So, that is need of physical characterization of the coating. Now, here comes we need some tools, some measuring device, some instrument, some equipment for characterization, and this is also, it is just not qualitative assessment that it is good or better, best, but also there must be some kind of quantification either in number or in percentage. So, from that we can have total assessment on the quality, whether it is a routine production or whether it is a improvement in the existing coating, or it is something new, something very new thing which is not at all known, and that in that case also we need to have all these characterization activities and the necessary tools and techniques for that. Now, from the experience and for the general use in by various groups, various people of various disciplines, we understand there is a numerous equipment for characterization those, but few of them have their extensive use, and we like to see how they do work and how they can be really used, make use of this from application point of view, so that one application engineer or the coating operator, coating technician, technologist can understand that what is the, what we have seen here, this what goes wrong with the process, and how this physical characterization give us clear understanding what we are lacking in the property and how this property can be improved through the improvement in the structure, and finally, it is the process where lot of correction has to be made. So, performance means it is the application engineer, and here we have the coating technologist here, and this is something, this structure of the coating, here we need an analyst. So, coating technologist, material analyst, then property understanding of the property, and finally, it is the application engineer. So, each has to understand what is going on in the upstream side and how we can really make use of this knowledge of this physical characterization to get correction here on this side, and also that will be reflected on this side. So, this physical characterization means actually analyzing the entire coating structure. It may be from the fractograph, from the cross section, it can be from the top, it is just a micrograph, it can be a metallograph, it can be X-ray, it can be quantification. So, with that we have to have one wing on this the needed correction, and with that we can straightway push it on this side for a expectedly a better performance. So, coating process and actual performance, in between we have this very important activity, and that is physical characterization. And here what we like to see, that there are certain tools, equipment for this physical characterization, and how they are working we can have a look. Now, one of the most demanding instrument, whether the ultimate application is materials, corrosion or mechanical, it is really in great demand, this scanning electron microscope, and this is one of the instrument the application engineer also must know how to read this instrument, that means the finding of this instrument on the sample, that one should be able to read, to record this message. Now, what is the message given by this instrument? So, from that we expect, so the analyst can generate lot of information here, and from that he can be able to speculate, or the application engineer can also see those data or the results. It can be a chart, it can be a image, or it can be a quantified value, and from that he should be able to have a very good speculation what would be the expected performance, or the analyst and the processing engineer, that means this coating engineer or the technologist, he should be able to understand how the process parameters, including the substrate preparation, that step should be properly tailored, so that the desired structure can be obtained without any problem or hindrance. So, here what is the basic principle? We can have a quick look to this. Before that we had actually optical microscope, but with the optical microscope this is the wavelength of light and wavelength of electron, that makes the whole difference. And with this resolution capability, that means how many lines can be separated per unit length, that is actually the resolution, and with that definitely this scanning electron microscope has a clear advantage. Now, this is scanning electron microscope which is conventional, but over that also we have FESCM, field emission microscope, gives still further resolution, and for those nanoscale, nanostructured coating, even if it is mechanically functional, if it is chemically functional, but it can be a nanostructured. So, in that case this field emission scanning electron microscope, that is one of the very powerful tool to judge the total architecture of the coating, how it is built up from the interface to the top atomic layer, and in between we can see the entire growth habit. If there be any flaw, then crystallographic habits, patterns, everything, then crack in the coating, some voids in the coating. So, the analyst should be able to record all these things from his observation. Okay. Now, what happens? It is actually the process, it is actually a sample is here, and that has to be put inside a vacuum chamber. So, it is actually vacuum chamber, and there we have one electron gun. Now, electron gun means we have all sort of peripherals along with the electron gun. That means it is basically a filament, and it is surrounded by one anode ring, and then we have like one well established electron gun, we have various magnetic and static lenses for focusing of this beam sharply on the substrate surface, or it is the coated surface, and also there must be some coil, magnetic coil for swinging the beam, for scanning the beam, so that the entire surface area can be recorded and registered with that beam. So, image will be taken, and this is going to be an electron image from this secondary emission or backscattered emission, and that gives us that resolution, and that will be useful for analyzing the entire coating architecture and morphology, and finally, the prediction for the performance of the coating, that has to be given from that particular image and picture. So, here what we see, that this electron specimen, so it is actually electron and specimen interaction. So, here from this electron gun, this electron falls. Now, as a result of this, what will happen? From there will be some kind of thing will emerge out, and these are actually one we call electron, secondary electron. We have secondary electron that is used for, we have also backscattered electron. So, this secondary and backscattered. So, this secondary electron and backscattered electron, they are used to record the image, SEM image, which we are normally examine, SEM image. So, this is one thing we get. Then we have a diffracted backscattered electron, and that is mostly used for studying the minerals, and in that case that is used for analyzing the structure of the mineral and orientation of the various crystallographic planes in that mineral. So, that is one of the important issue, and that is backscattered electron. Further to this, we also have characteristics X-ray. It is a characteristics of a particular element. From this periodic table, we have all this material, there is some gradual variation along the row, and there is similarity along the column or the group. So, this X-ray is a characteristics of such variation in the element. So, this X-ray itself becomes a representative on one element if we can detect it during this bombardment of this sample by this electron, and this characteristics X-ray can be captured and it can be processed to get some information about the material of construction of this coating. And here we can say one thing, that it is actually this scanning electron microscope that can be also used for bulk material. It is can be organic, inorganic, biological, but here we are mostly interested in metal, few of those non-metal, some ceramic, hard metal and their combination. So, it is mostly in our case it is inorganic, and if it is mechanical sample, naturally it comes from within the metal group, alloy group. We can have hard metal type material, that means some transitional carbide nitrides with some of the metal as the binder. Even we can have straightforward ceramic, for example, aluminum oxide and silicon nitride, silicon carbide. But wherever this examination is necessary, this instrument with all those outcome, that means this secondary electron backscattered characteristics X-ray, they are the characteristic feature which can give us the ready hand information about that coating. Now, here how we are going to look into this. Now, what we see, let us examine. This is actually a secondary electron microscopic image of a diamond coating. So, what we see here, that these are the diamond crystal. Through this SEM image, one should be able to recognize these fine crystals which are part of this coating, and this is deposited by this hot filament technique. So, that is one thing, but what this SEM gives us, actually if we see this one, naturally we find a difference between this. So, that is the reading from SEM. So, this image and this image, there is a difference. So, here we see a well developed crystal with a well defined crystal habit, which is expected from this coating activity. It is a low pressure synthesis. We do not have any high pressure to facilitate diamond formation. However, here we do not have such favorable situation. This is very adverse situation. The outcome is that not fully grown and it looks like that crystals are not at all grown. So, it is something like very towards the amorphous side, some of those. So, just looking at one can find out the difference between these two. So, here we have to train ourselves that how these two image can give us that message that yes, this is one good coating, well developed, and this is a poorly developed morphology. And if we know there are certain process parameters in diamond coating, and one we know that it is actually filament from hot filament to the substrate distance, and in that this SOD which is 6 millimeter, 3 millimeter and 4.5 millimeter, and if we vary that one we have different result. Say for example, we can have just a quick look, this is the filament and there is the substrate if we recall, and this is SOD. So, this experiment give us a clear indication that with this 3 millimeter it is so delicate, and this delicacy can be understood just by the image produced by ACM, and here we can see well developed crystal, individual crystals are large than this one, and that will also get from ACM, but this is not covering fully. So, this is actually a carbide substrate. So, this is an exposed carbide substrate, it is fully covered, but not a good morphology. This is one of the very good morphology, and here we have discrete deposition. That means, what we can find here that this ACM image clearly give us the information that nucleation centers or nucleation site. So, nucleation density is not quite high, but in this case nucleation density was quite high. That means, so many points were available where the diamond could grow, and it can be inferred from the process technology. If one really handle the process of this substrate preparation, one may have a very good reasonable speculation that it was also the good seeding. If we have a good seeding with the diamond seed, fine diamond dust covering all the pits in the substrate, then perhaps we can expect such thing, and here this etching of cobalt and proper seeding with diamond, that was not very good, and as a result we have end up with such thing. Now, the whole idea here to show this picture only to impress upon the fact that with this ACM picture we can get lot of information about the quality of the coating, and also with our experience we should be also able to make certain reasonable remark or observation, it is with reason not without reason, about the process itself in the upstream side, and what are the preventive measure, corrective measure has to be taken on that side, that can be well understood from this ACM picture. So, this way lot of possibilities ACM can open up, and this is just by one way of illustration that we can see the utility of ACM in examining the morphology of a diamond coating, which can be grown by low pressure and low temperature synthesis using this methane, hydrogen and a filament, and that is called HFCVD. Now, here we can give another example that this is the diamond coating, and again it is the ACM picture. Now, it is the cutting tool, and if we know that this is going to be the cutting edge, this is the top face of the tool and that is the flank of the tool. The surface is relatively rough compared to any PVD coating. This is also a fact. However, it is well covered, that means from this we can also have a good inference that the process technology allows us to have a full coverage of the cutting edge, and it is well built cutting edge, it is integral, this coating is integral with the substrate. So, this picture, this recording of this picture is so essential with much clarity that this is the face and flank of the tool that is well built with this coating, and there is apparently no micro void or cracks, and to examine into deeper we can go for even higher magnification, but if it is so needed, and scanning electron microscope with this high resolution power that can give us that leverage, that with that we can make lot of analysis on the quality. Now, here that is one weakness or fault in the coating that is also identified. So, this is a nice coating deposition which is recognized by SCM, but this is at the same time is also a fault with the coating. What we can see, the remaining part, the coating is more or less uniform, that means the crystal size is more or less uniform, and that is one of the requirement we have mentioned at the very beginning of the lecture. But here what we have seen, that unfortunately we have too large crystal. So, it is like a mountain over this base, and these are the odd element in the whole matrix, and this is going to make a fast contact. The beginning they will make a contact or make some deeper scratch during cutting or some processing. So, this is not a very good sign in the coating, and this is to be avoided. So, this SCM picture can reveal so many things apart from the crystal size, this uniformity, this void density, but it can clearly shows this outgrowth. If there are certain pinholes, it can also happen during this coating deposition. Sometimes certain areas, because of the very strong passivity, is not covered at all by this coating. That means, this coating does not get attached to that, and that is called the sticking coefficient. So, this lack of sticking coefficient can also make some pitting or void there, but that can be also recorded by this SEM. Now, what we see, now we go to the cross section, that means it is a fractograph. So, this is also the SEM which gives us that picture. So, this is important in that this picture give us a clear idea about the coating process or the coating technology. That means, the coating process itself is capable of just not coating a flat surface, but it is just the two surfaces, that means one face and flank, that means two surfaces at right angle, and this is the edge. This is the edge, that means if we go to the first slide, this is the edge. So, if we make a cross section here by fracturing, then we get this picture. This is the picture. So, it covers, and apparently there is no fault in the interface, but still with higher magnification we can look into that what is the fault, how this interface is built, that can be also possible. Then comes uniformity in the thickness of the coating. So, that is here we find the thickness is little more compared to the thickness on this side. So, that is also one thing one has to look in. And what additionally we can see, the substrate itself. The substrate is a hard metal in this case, of course. So, this is tungsten carbide and cobalt. So, the toughness of this substrate is extremely important, and for that, if when we see that fractograph, on this fractograph we can see the average grain size which appear on this after fracturing. So, this SEM picture covers the entire information on this coating up to this surface, and there we can see how this coating with to what extent this coating is an integral part of this substrate. Now, here what we see, it is actually this interface, somewhere the picture has been taken. So, this is actually the interface, and from this point to this point, that is the coating. So, we can assess what is the coating thickness, and with proper clarity of the picture we can also see the morphology of the coating. So, it started from this surface. So, that was the interface, and then we have some seeds also. So, with this we can also see after seeding, if we take a picture, even it is possible that in the pores or voids, because of this cobalt etching, if we have these pores and voids, there we can find that if these diamond seeds are really captured in those pores and voids, because that from that the tree will grow, and then that will spread its branches and it will cover the whole area, and we have a deep anchorage inside the cavity. So, all those things can be given by this SEM picture. Now, here also it is something very interesting, that when the material, it is a tool top surface, if it is one non-compatible tool, the chip gets stuck. However, when it is a diamond coating, this chip does not stick, but we can also examine how long this coating can survive. Here we can see this is the substrate and that is the coating. So, it is also certain limitation on the coating, that after doing some useful work, after doing all the machining, damage is not much on the flank, but it is actually the chip is flowing on this side, and because of some weakness at that point of time, the coating got flecked in this area, then exposing the substrate. But in this case what we see, this is the principal flank side, only here little bit of chipping, but this side this coating is still retained. So, what we see in this here, that this side which will be actually follow up zone, this side that does the machining, and this side it is a follower, but that is the place where one has to see that this is the place where the workpiece is in continuous contact with the coating. So, coating is not yet has gone. So, still it is written, and that is why we expect a very good finish that can be also recognized by SEM. So, we understand the role of SEM. Now, here we can find very interesting picture. So, this is also SEM, study with SEM, and how does it help the coating technologist to understand, or the application engineer to understand, that when it is alone MOS2 or when it is just not MOS2, but it is MOS2 molybdenum disulfide plus titanium nitride. So, here physical characterization is extremely important in that, because that is a new development, and we know MOS2 in its individual entity, it is a lubricious coating, and it has some limited application. This type of structure or morphology, this has a limited application in under vacuum environment with all those satellite mechanism, and in those cases this is a good coating what we have seen, but our purpose is to improve its performance, so that it can be used in one of the most important tool, that is cutting tool, use of MOS2. But we know that titanium nitride, that is already well known as hard coating. So, on one side we have a soft coating and on the other side we have a hard coating, but when we put them in right proportion, then what is the outcome? Now, this outcome is immediately that message is sent by SEM picture. Now, here we see it is like a globule, it is like a porous spongy structure, it is not so densified. However, when this titanium nitride and MOS2 they are combined in right proportion, what we see this grain refinement and densification of the coating, and obviously one would expect that this coating will be better than this one, from this cutting point of view, and that what we see coming here, that this physical characterization here, this architecture physical characterization, that give us a clear message or a clear indication that this coating would be leave some promise. And what we see here, this ACM, what we see here, that this is the initial titanium coating followed by one MOS2. Here also we have a titanium nitride coating followed by this MOS2 titanium nitride coating, and this fine layer, that is also one titanium. So, this ACM image here also gives us this, it is such an effective tool that here we can separate out, this is TI layer, just like it is magnified, and this up from this point to this it is titanium nitride, and this to this it is a mixture, that means it is a co-deposition of MOS2 plus TIN. So, these are the picture for the field emission ACM, which gives a better clarity than ordinary ACM. Now come very important tool, and it is actually this Raman spectra. Now, here this is very useful if one is engaged in deposition of diamond coating. There are numerous use and application of this Raman spectroscopy, but when it is a hard coating or super hard coating, one can just go for use of this Raman spectroscopy with a very clear objective. Now, we see how this work. It is actually, we can describe it best, work on best its the principle is based on spectral distribution of inelastically scattered light. So, this is actually, and then what we see here, the molecular species in all phases of matter are fingerprinted. So, this is actually the wavelength or say frequency of that particular signal or from that spectrum, and that is a characteristic of a particular material. Now, how it is becoming so important when we deal with hard coating, particularly it will be seen here, that we want a diamond coating and without any non-diamond phase. Now, there are certain frequency which will be given by say 1331 to 1337 per centimeter, that is the wavelength, and with that we expect a sharp peak which corresponds to diamond according to this Raman spectrum. However, if we have some non-diamond phase which is amorphous, then we also expect certain phase around 1581 per centimeter, that is the Raman shift, and this way we can get a non-diamond phase. So, we have another coating deposited in another condition. So, if we keep this picture side by side, then we see that this is a coating free of that non-diamond phase, which will be a weakness of diamond, and here we have this kind of thing. So, accordingly, this is a very delicate process dealing with CH4H2, that flow ratio, the process pressure, the substrate temperature, but finally, the outcome is here, and this is actually this Raman spectroscopy. From that we get to know what is the quality of the coating. It is just not ACM or X-ray diffraction diagram, but it is actually this Raman shift. From this Raman spectrum we ought to know, we get to know what is the quality of the coating. So, all the effort should be made to have a spectrum like this, even better, with no hum formation, and that will give us a clear idea about the quality of the coating. So, this way we can find under various conditions with different substrate, different seeding, we can have a high growth coating process we can have grain fineness. So, there can be lot of measures to improve or to improve the yield of the process or to improve adhesion or the basic property of the coating. But finally, before we go to any further step, this diagram will definitely point at that particular direction, that whether we are with good diamond or poorly grown diamond. Now, we have what we call electron microprobe analyzer, electron probe microanalyzer. Now, this is can be used along with SEM in the same chamber, or we can have a different equipment for that exclusively for metal analysis, and it is a quantified value. It is exclusively used for recognizing the purity of the metal for any construction work from metallurgical point of view, from material science of point of view, and also from application point of view. So, it is quantitative element analysis and it is called wavelength dispersive spectroscopy. So, we have actually two types of spectroscopy, one is called energy dispersive, another is called wavelength dispersive spectroscopy. Now, let us see how does it work. Actually, we can see, we know that this is one equation what we call 2D sin theta Bragg's sine law. Now, here that is the wavelength of the X-ray, that is the actually the distance between the two planes, that is the space lattice, and this is actually the angle along which we can get this thing. So, that means this value of lambda and this sin theta, they are related with this 2D, or say for this value of lambda, if this d changes, then also this value of sin theta changes. So, this way what we see in this case, electron beam, it falls from this electron gun and this is the sample. Now, when we have mentioned about SEM, we have shown that we have this secondary emission of electron, backscattered emission of electron, those are used for imaging, and we have this characteristics X-ray, and this characteristics X-ray that is used for detection of this element, and this characteristics X-ray that is a typical of a particular element, and that is also given by this one. So, here we have this wavelength and this is also connected with this d and sin theta. Now, let us have a quick look how this principle, how does it work. This electron beam comes from the electron gun, it falls from on this, and we have emerging X-ray which is emitting from this surface, and there we have a detector crystal, and with this detector crystal what we see that this will be there and that will be a reflection here on this side, and that will be detected and captured here. Now, it is interesting to know that all these things are placed on this circle, and that is called Rowland circle. So, what we can see, these are on the diameter. So, whatever may be the angle theta, then ultimately this ray is going to reach this detector. Now, what we can see, depending upon the value of theta, this for the lambda, this value of theta will change. That means, if this lambda changes because of the a particular material, this lambda will change, and that will be detected by this sin theta. That means, if we change this orientation of this crystal, then a particular wavelength will be captured and that will follow this particular equation. So, that will correspond to a particular d value and this d value will be a characteristics picture of feature of one particular element, and this way we can have detection of different elements which see except few of those very light elements, but most of the elements it can be detected, and this beam, this detector, that can also probe over the surface. So, with this what we can find, not only the compositional composition, quantification of the composition, say it is TiCN. So, value of, for example, value of titanium Cn, or say for example titanium carbide. So, it should be, say it is 80% and carbon 20% by weight, or if it is titanium nitride, for example, it will be 70% and 23. So, this way lot of analytical activity can be done, but this thing we can use to our advantage just by analyzing the coating surface from the top, or it can be done this way, that say for example, we have the coating something like this. There we have aluminum oxide coating, and then we have titanium carbide coating, and then we have this substrate here. So, this is aluminum oxide followed by TiC and followed by the substrate, and the beam can scan over this. So, if we look into this, this is the distance it travels, and over this if we have the ordinate which shows the concentration, then what we can find, that at this point we can have this increase of this aluminum oxide aluminum, and then it will fall immediately because it is a thin coating, and then comes the concentration of TiC, that can go like this and that will fall, and then what we have here, we have the substrate, and there the percentage of, so this percentage will go like this because tungsten carbide plus cobalt. So, this way we can find out the diffusion between the interfaces or the thickness of the coating. So, we can apply this principle of detection, and that can be very well used for characterization of this coating, in that it can be one of the instrument for quantification in a point, or we can also have a line scan for analysis of this coating along the interface, along the depth. Now, we have EDS, that is energy dispersive spectroscopy. So, in this case what happens, it is also the X-ray, but it is no more the wavelength, but it is the energy. Actually, the EDS detector that absorbs the energy of X-ray, and it separate those into an energy spectrum. That means, energy which is released as X-ray, that will be absorbed, and there will be a spectrum, and this spectrum is actually typical of all the elements which are present there, and that will be then that will be a spectrum separating those. So, this is very important, it should be able to separate, and finally, what happens, this energy of individual X-ray, that is converted into electrical voltage of proportional size. So, this electrical voltage, this X-ray, that is typical characteristic of one individual element. So, from that it is possible to find out the element which is present, what is the percentage, and also the combination, that means it is the percentage of element and also it is the atomic ratio, in what atomic ratio it is present in that volume. Now, in this case what is important concerning the activity in the coating. So, there are certain thing what should be looked into, say for example, its application WS2 coating or molybdenum disulfide coating. Now, these are of immediate interest, but also we see also we have seen that in this case incorporation or oxygen gets into that, and that makes this coating inferior and this quality falls drastically. So, in this case whatever may be the issue, only detection of oxygen is extremely important. Now, it is a typical application of this EDS or microprobe for this particular coating. It is the detection of coating, just like Raman spectroscopy we have illustrated that that is extremely useful for diamond coating, but this is also extremely useful. Now, we can also have say XRD. Now, XRD means X-ray diffraction diagram, and it can be also GIXRD, that means it is for the film. Now, what we see in this case, it is also we know that this is n lambda 2d sin theta, that is the Bragg's sign law. So, depending upon the X-ray which falls on this surface, this X-ray from the X-ray source it is falling and there will be a diffraction. So, this X-ray there will be a diffraction and the detector will detector is going to capture this diffracted ray depending upon the value of theta. Now, depending upon the element or the phase, the value of lambda will change, and since it is actually the 2D, that means the spacing. Now, depending upon the crystallographic spacing, this lambda will be connected with 2D and sin theta. That means, if this d changes the spacing, then a particular lambda, particular value of d, that is connected with this sin theta, and accordingly in the XRD diagram where we put 2 theta, and we can get typical peaks which shows the very existence of a particular phase, or it can be this theta that can be measured here, or it can be in another place. So, this is also typical of a particular coating, say for example, WS2. In this case, what we are interested in 002 basal plane, and this XRD diagram that will give us clear indication of this 002 plane depending upon the value of 2 theta. So, for a particular value of 2 theta, if this peak is indicated, we can immediately recognize whether it is 002 plane that is parallel to the substrate surface. If it is not the case, if so, that is comes at the lower angle, there are other plane which are H plane or 101 which appear at a higher angle. If those thing appears, then that is also a clear signal that this coating cannot be a good candidate for this lubrication or lubricious property it cannot give, and it cannot have the satisfactory performance in that particular activity. So, these are the few illustrations and examples. So, this is actually how this XRD diagram can be used. It can be used with a one particular coating having different crystallographic planes. So, in one case maybe it is 1 plane prominent, but it can be also 100. So, whether it is strongly textured coating or it is a coating with a what we call equiaxed, that means that type of coating that can be also detected by this XRD. So, we have seen that this instrument of physical characterization, which are scanning electron microscope, then XRD with this GXRD, that means this grazing incidence XRD for analyzing the film. Then we have Raman spectroscopy, we have this energy dispersive analysis of X-ray. These are the few tools of physical characterization. These are commonly used for physical characterization of the coating, in particular for those mechanically functional coating, and which are used for all sort of wear part friction reduction tools of manufacturing. For those, this physical characterization is extremely important, and if we get a favorable response from this physical characterization, then only we go for all sort of mechanical characterization and followed by this performance test. So, this physical characterization is one of the very important step between the processing of the coating and finally evaluating the performance of the coating.